Hello, hi everyone. Today we are going to discuss about how we can find the application slowness, and we have discussed about network latency, and now we'll do one use case how exactly we can find a network latency and what are all the key things we have to consider for network latency. So we're going to discuss about that, and along with that, we'll discuss about how exactly we can spot issues with BGP. So what kind of information it's been exchanged, and how the Wireshark is going to interpret those details in Wireshark. And this is all about not too much with the network topics. So here we can see how we can leverage the Wireshark to see the details for specific protocols like BGP and IP precedence value, and what is IP precedence and how Wireshark going to interpret the IP precedent value, and a little bit background about QoS. And in the upcoming classes, in the next classes, we'll do a lab for QoS, and we'll discuss about how EIGRP exactly works, and what kind of information that's been exactly exchanged, and how Wireshark is going to interpret those values. So we're going to discuss about everything. So to start with, let me start with the application response time. So to do that, let me open my paint. So examples here. Let me take source and destination. So we all know that whenever the TCP connection establishment happens, it should be a successful three-way handshake. And this is source. And this is destination. SYN, SYNAC, and ACK. So in the Wireshark, we'll look into these values. One is the delta time. Also, it is used to calculate the RTT, round trip time. And along with that, we use a time value, time since the previous displayed value. So these are all the key things we'll look into in the Wireshark to find the network latency. So along with that, what are the other key things we should know about network latency? If you look at this, when we calculate the round trip time, so this is a client. So I send the TCP SYN, and to receive my SYNAC, so all it takes is for my complete round trip time, it takes 30 milliseconds. For the complete TCP connection establishment, it's 70 seconds plus 30, so 100 milliseconds. Example, I'm saying. So this how the round trip time is calculated on, okay, my source, the client, it's an a TCP SYN, and for that I receive a TCP SYN. So example here, I started the connection established with 30 milliseconds. That is the underlay connection or the transport, the TCP, it takes 30 seconds since I send a TCP SYN, until I get a TCP SYNAC. So it takes 30 milliseconds. That is my network round trip time. That's how we calculate. So where exactly the application comes in? So how I can find it's an application slowness? So the logic behind that is something I have to look into my network round trip time. And if my network round trip time says network round trip time, it says 30 milliseconds. And after this connection establishment, your actual HTTP request happens. So from the client, once this connection is successfully established, next comes your HTTP GET request from the client. For this HTTP GET request, I should get a reply from the server. That is HTTP okay. So after this, my actual data transfer happens over HTTP. So this is layer 7 and this is layer 4. So here my HTTP, for my HTTP request, if it takes 20 milliseconds, sorry, for my HTTP request, it takes example 50 milliseconds. For my HTTP request, it takes 50 milliseconds. So my actual network round trip time, that is the time which is taken on TCP, it is 30 seconds, but my connection established successfully. It means my network is stable and I get a request within 30 milliseconds. My network round trip time is 30 milliseconds. Whereas for my HTTP request, it takes 50 milliseconds. So the 20 milliseconds, it's greater than that 30 milliseconds. So it doesn't mean that my network has some problem. It is not something problem with the network, it's something with the application. So this is how we can figure out. So in the capture, we'll see how exactly we can differentiate those. Yeah, we'll talk about that. So what I'm trying to say here is, so the network round trip time is different from your HTTP round trip time. So this is a layer 7 and this is layer 4. So as far as your layer 4 is good and there is something problem with the layer 7, then you have to check who is taking longer time to respond. Is it a client or server? So, but the first thumb rule is whether I have to, the takeaways, is it a problem with the network or it is a problem with an application? So for that, you have to be familiar with what is delta time, what is round trip time, and how round trip time is calculated, and what is initial round trip time. Example, if my communication happened with 30 milliseconds, and maybe in the 10th packet in the source, again for my TCP connection, if the value jumped from 30 milliseconds to 50 milliseconds, so it means that my network has some problems. So I have some bottleneck. So always I have to compare my initial round trip time. My initial round trip time is the when exactly the TCP connection establishment happened. Back then, if I had some problem and my time taken has been increased from 30 milliseconds to 50 milliseconds, so that is something I have to look into my network, that there could be some problem. We have to figure out that. But even for all the communication until your TCP fin packet, if you see your network round trip time that stays and sticks to 30 milliseconds, it means that your network connection is stable and there is something problem with your application. So this is how you can differentiate, is it a problem with the network or it is a problem with the HTTP. It's a layer 7 or layer 4. So this is how you can differentiate and you can spot exactly where the problem is. So now let's see a capture. So let me open up this. So the very first packet, we know this is SYN. I send a SYN packet from, because this is a client, from the port number. I know this is a client random port number, and 80, this is for HTTP. And I get a SYNAC from the server. The server is 10.0.0.100. I get a SYNAC, and if you look at this, both allows the SAC, selective acknowledgement. So here you can see that, and even the TCP options, you can see the selective acknowledgement. It should be permitted on both ends. So now my connection establishment happened successfully, and the client sends a GET request. But before that, when you look at this, this starts with the delta time starts with 0 milliseconds. And then for my SYNAC, it takes 105 milliseconds. So this is my initial round trip time. And if you actually see this, I send a GET request, HTTP GET request, and it continues, and the server sends an acknowledgement back. Then it continues, and if you exactly spot here, for this HTTP 200 OK, this is from the server. It took about 20 milliseconds here, sorry, 20 seconds. So all the values beyond this period is milliseconds. So here it takes 20 milliseconds. But if you look at the initial round trip time, so example, if I take this TCP, and if you have to go to sequence and acknowledgement analysis, and if you see the initial round trip time, it says is 106 milliseconds here for my TCP connection. So it means that I don't see the jump in the TCP, but whereas for the HTTP, I see a jump of 20 milliseconds. So who's doing that? So I send the HTTP GET request, but after 20 seconds, the server is actually sending a reply back. And if you scroll down, the server is doing a reset. So it might be busy with some other communication and it is not ready to respond at this point of time. And if you see, there is a lot of TCP keep alive. So this is the client, and the client keeps sending the TCP keep alive, and for that the server is sending a TCP keep alive back. So it is something like the TCP connection should be opened. It says that my TCP connection is active, but it takes 44 milliseconds for a client to send a reply back again. So here the problem is the server is busy server and the application has a slowness. So what are the other key things when you have to consider for when you reach out to your application team? So what are the key things you should ask them? So if you look at this, the key parameter is I have calculated my initial round trip time. What is the time taken for my TCP SYN and SYNAC? But whereas for my application request and application response, I see a jump of 20 milliseconds. And also I have to check, is it the server is connected to the backend DB server or any kind of server, or is it some kind of a load balancer you're trying to establish a connection? And the backend services that's running on the backend server from the load balancer VIP to the backend servers. It establishes another TCP connection. Is it a problem there? So you have to do a capture even in the middle, and you have to calculate, is it from my server to the backend server? What is my round trip time and what is my application response time? So we have to look at all from all the angle, from from every angle you have to look into it, and you have to do a capture. But the key thing is you have to differentiate what is the difference between the TCP round trip time and the application round trip time. And also you have to look at what is the DB connection it has, or it is a load balancer is something connected in the middle. And you have to do a bidirectional capture, and you have to see where exactly the problem is. But the key thing is you have to, the takeaway is you have to know the difference between what is the TCP round trip time and the application round trip time. So you can figure out where the problem is. And if you have to go through some other options, like do I see a keep alive, TCP keep alive? So if you look at this, the client is keep sending a TCP keep alive, and I get a reply back, but after 44 seconds it sends a keep alive. So it means that the server is not responding. And also you can make use of your other fields like your TTL, your acknowledgement fields, and you can make a comparison as well. But it's pretty evident that I keep sending a TCP keep alive for the server because I am not getting a response from the server. And later on, at some point of time, the server is resetting my connection here. So there is something you have to look into this server first. Is it a lot of reset happening for other clients, or is it the reset happening only for my IP address 172.16.0.13, or it is doing a lot of resets there? And I also I have to check, is it a lot of keep alive happening on the server end for other HTTP connections as well. So this is the key thing you have to, you can find your application slowness with this logic. So let's do a normal capture and let's see what is the time taken for it. So for that, let me open up the server. Just give me a moment. I mean, have some problem connecting to this server. Just give me a minute, guys. Yeah. Yep. So if I do a DNS matches Google, so I'm going to see my DNS request here. So this is my first request here. So I want to find an
Please
IP
share your
address of,
screen.
okay. One minute. Actually, we have some problem here. I don't know. I lost access. 1 minute, guys. Hi, Gilmon. Hello. Hi, Gilmon. Can you hear me?
Hello. Hello, Arjun. Yes, I can hear you. Hello.
I don't know. For some reason, you became a host. Can you
Oh,
make me a host? Yeah.
oh, I don't know how that happened. Just bear with me. Sorry.
No problem. Yeah.
Okay, I've done that.
Yeah. Thank you. Yeah. So I think everybody can see my screen, right? Okay. So if you see this DNS queries, I want to find the IP address of google.com. So for google.com, I got a way record here. So I got an answer here. So I'll copy this as a value. IP dot address. So I'm going to filter only the IP address of google.com. If I go to any conversation, so if I go to conversation filter and TCP, go to your conversation filter TCP to check this. So it is broken somewhere in the middle. My calculated window size, my acknowledgement. Okay, from here, if you look at this for your HTTP, let's take and no HTTP connection happened for the source and destination. So this is my device. So it has taken 37 seconds for a GET request. And if you look at this, all my device, it's taking 46 milliseconds. And if you compare the value with TCP, and if I stop the capture, so this is the IP address. So let's check for only TCP. So if I go to conversation filter TCP, if you scroll down here, I can see for the TCP, it goes from 20, 26 millisecond, 18 milliseconds, 17 milliseconds, and 18 milliseconds. So it means that definitely I have some slow connection here. So how to find who is doing the slowness? If you look at the other TCP conversation, if you give common as a TCP, if you look at all my TCP connections, I don't see a biggest jump here. If you look at your delta time value and my time value, it's not showing anything abnormal, or it's not the time taken is not jumping even for a second here. But for that specific conversation, my delta time has been increased to 1740 milliseconds. So it means that, so when I establish a connection, HTTP connection, I see a slowness. But whereas for other TCP connection, if you look for other IP details here, only TCP, I don't see anything here. But if you look at this particular IP address, and HTTP, if you look at the HTTP requests, I see a lot of latency for my HTTP requests. And if you look at this common public IP address, I don't see a biggest jump in the public IP address, but for the internal IP address. So for my PC, it takes 46 milliseconds for me to do something. So it is something that I'm doing something here. I'm searching for the options here. I'm not doing a proper, I'm not very active with my HTTP connection. That could be one problem. And other problem would be really if it is a server and if you clicked on something, and if the user is not doing anything, and if user is active but the server is not responsive, and if the server is busy, then you will definitely see the slowness. So this is just to find how we can compare the the round trip time for HTTP as well as for the HTTP. So from here you have to figure out, like in the same way you have to figure out for other issues. So you have to replicate and you have to go through step by step and you'll get to know about that. So the main key thing is how we are going to differentiate the round trip time for HTTP and TCP. So now let's see use case for BGP. So I'll give you a little bit background about BGP for the same. So there are two different protocols. We all know about this. This we know. I mean, the routing protocols is used to exchange the routing information. And there are two classification. One is IGP, one is EGP. IGP stands for Interior Gateway Protocol. EGP stands for Exterior Gateway Protocol. So why we are talking about all this? So I just want to give a background about that. So IGP, that's further classified into all your EIGRP, the most commonly used, and OSPF. And for EGP, there's only one protocol, BGP, and that is most commonly used. So I think the ISIS falls in the category of BGP, but here we are just talking about BGP. So what is the interior gateway protocol? Okay, so this is my network. This is my autonomous system. I mean, this is your company and you have your own, WAN connections. So you are managing this WAN and this is IGP. And BGP is further classified into two categories: IBGP and EBGP. So by design, so if you are using an IBGP, it should be mostly they use for the core switch and the hidden router peering. For that we use IBGP. So this IBGP routes cannot be routed externally. So that's all stays within your network. So only your head end router and your ISP, they both will be talking and exchanging routes on EBGP. So this IBGP is interior gateway protocol. So most of them, they use EIGRP or OSPF. This is the most familiar and most commonly used routing protocols. And the BGP, why we are talking about BGP that purely work on TCP. If this particular router, if this both router has to establish a connection, so it has to send a SYN. For the SYN, I have to get a SYNAC back. And then again, the source will send a acknowledgement back for the TCP SYNAC. So once this TCP connection establishment happens, in the BGP updates, it will share the NLRI information, that is network layer reachability information. So for this device, the network example, I own a network 10.0.0.0 and I own a 20.0.0.0. So in a BGP update, it will send the network layer reachability information. In the same way here, it will share its network layer reachability information. It is that, so it shares the network information. Along with that, inside the network layer reachability information, you will see the subnet mask, the ACE number. So all been exchanged. So why we are talking about all this? So if you know about all this, and if you peel out the capture in Wireshark, and if you see, is there anything, the subnet mismatch that is stopping your connection, or is it something, there some here particular ACL they have applied to TCP SYN, if they are blocking the TCP SYN, so you cannot establish a connection. So both side the TCPs, both three flags has to be open, since SYNAC and ACK. Only then if the connection establishment happens, after which your BGP updates with all your NLRI information, everything will be exchanged. And now let's see how Wireshark is going to interpret all those values. In our active capture, I'll show that first and we'll do a lab followed by that. So if you look at this, the very first packet, the source is sending is a SYN. For that SYN, I have to get a SYNAC. And then for the SYNAC, it acknowledges it back. Then it sends a BGP open message. And if you drill down the open message, if you can see the BGP open message type, and you can see the autonomous system number, and you can see the BGP identifier, the IP address of the source. And it also talks about the capability of route refresh. We'll talk about that later. But it shares all this information, and along with that, inside the BGP, it has the capability to share all this parameter details here. So I get a reply message from an open message, keep alive. So it means that my TCP connection is still active. And this is the actual update message from the remote destination. And if you look at the path attributes, it says IGP. And if you look at this, this says it's a next hop. This is my next hop. And along with that, the local preference value, it says the local preference. We'll talk about that, what is local preference. But if you see, you can see all this attributes inside. And along with that, we can see the network layer reachability information inside. If you open it, you can see what is the network address and what is the prefix length. So you can see your next hop, your local preference value. You can differentiate both the NLRI information. You can check, is it something your subnet mask is incorrect? You can go and verify the same. It will give you a bird's eye view of everything about your BGP, and you can see the AS path. It says it takes 65100 and 65200. So it says my next hop is 1.1.1. And again, I see BGP, network reachability information, path attributes. All this value is very useful to troubleshoot the issue. So if you look at this, this is a successful TCP connection establishment happened, and both established a BGP connection. Then it's exchanging the updates, and inside the updates, it's sharing its NLRI information, and it is sharing its autonomous symbol system, and it's sharing its AS path, all this value. So you can check end to end. Is it something problem with my parameters? Is it something wrong with my updates? It's not something I should look at. And if you can see the keep alive packets, a lot of keep alive packets, why there is a latency here. Because 41 millisecond and for 18 seconds and 41 seconds, it's giving an keep alive. If it is sending an update, that can be considered, because after 18 seconds you made some changes in your domain, and you made some changes in the router for specific to the BGP. So after the 18 seconds, I mean, you made some changes, and after 18 seconds, it sends an update back. So the update is coming on. So you're doing some configuration. But if you look at this keep alive, it's taking 41 seconds. So that is bit higher. So you have to look at why I get, after 41 seconds, I got a reply from 4.4.4. You have to look at the router. So this is how BGP looks into, and how Wireshark can interpret those values, and we can use it for troubleshooting. So the key thing is the BGP, the BGP is the first thing is only if your TCP connection establishment happens, your BGP update happens. So if your TCP connection establishment fails, and your BGP will not work here. And we talked about IGP. So the IBGP that comes under IGP, this all works within your autonomous system. And the only protocol which talks to your ISP and the head-end router is EBGP. It has to be a EBGP neighbors, and it should share its NLRI information, network layer reachability information, between both. So this is how a successful adjacency looks like in BGP. And let's see what we can do with the lab, and we'll do a capture there. Let me stop this capture. If you look at this, I made a very simple config. I have two interfaces on router 2, fast ethernet 0/1 and fast ethernet 0/0. So the very first thing is I have to check my interface status and protocol is up. And then if I give show run section BGP, pretty simple config. So very first thing is we will define the AS number and then the network. What I have, I got two network here. So 11 network and 10 network. I didn't advertise the 10 network, but I have advertised my loopback IP address here. Same way, if you look at this config, I have only one IP configured on router 1 on fast ethernet 0/0. So this is just something I have given the same point-to-point connection. So it is just 10 network. I have given IP address of it. And if you look at the BGP, so I have advertised my network and I said my neighbor, it's 10.0.0.0 network. So it's in my neighbor, I said it's 10.0.0.1 and remote AS is 1. And I have to, this is something I'll advertise. So I have to make a neighborship and I have to advertise the network. Only then your connection establishment happens here. And if I give show IPBGP, it says 10 network, the default weight value, and I stands for IGP. If I go back here, show IPBGP summary, it shows my uptime. It shows the number of messages I sent and received, all these details here. So it prefers the directly connected route. So now let's go and shut down a port and let's see what is the message we see there. So you can see 10.0.0.1 is doing a retransmission. Because the port is down on router 1 and it is 10.0.0.2. So it is continuously sending a retransmission. So it is hard down. So I established a BGP connection and it is down. So it is sending a keep alive to make the session open. 10.0.0.1 is on the remote end. It is sending a keep alive and you can see I'm not sending a keep alive back. But if I go back, I gave a no shutdown. And now let's see the BGP update. It says the next hop is 10.0.0.2. It's a default local preference, and then NLRI information I can see here. So when it was down, so it is sending a retransmission and it's sending a keep alive 10.0.0.1, but I am not getting a keep alive back. But if you look at here, again, the 10.0.0.2 is replying back for the keep alive sent by 10.0.0.1 here. And this is evidence that the port is down, it is coming up, so it sends an ARP. For the ARP request, I get an ARP reply back. And the gracious ARP, it says, this is my IP address, I am back. And for the ARP request, it sends a reply back. So you can also compare the MAC address for the same. So this is how you can, this is just an overview of it. So you can dig deeper to find other stuff. But as we discussed this in the successful adjacency, the BGP updates, if you look at this, you will get you'll get all this information here. So if I suddenly I see there is a keep alive packet that's coming in, so it means that I made a TCP connection establishment successfully, but I didn't get a reply back. After some time, there is something problem with the device physically hot down. That's why I send the keep alive, right? So there is something in the middle in the network path. I lost connection to it. So for that keep alive, I get to keep alive back, and after in the BGP update, I see the NLRI information, and I'm running IGP. It differentiate with the AS number. So in the NLRI information, I see the attributes. What is the information? What is the network update? And if you see, always it uses a port number 179, TCP port number 179, and it says it's a BGP update. And since I don't have an AS path attribute configured, I don't see anything AS path. But if you compare the BGP connection adjacency, what we discussed earlier, you can see your AS path value here, 65100. This is the AS path because it's been configured with path attribute. So all your path attribute you can see here, your local preference, your origin, your AS path, all your path attribute. BGP has different path attribute, right? So you can look into all the attributes. Since this is not BGP deep dive, I'm just showing how Wireshark can interpret those values. So you will get to know about your weight, your local preference, your AS path, your med, your matrices, all this information you can see. This is pretty helpful when you do a troubleshooting, and you'll come to know this is something very simple, simple false bug we did, and we try to figure out and who is doing a retransmission and who is sending in keep alive. So it is something that who is sending in keep alive and who is not is sending a keep alive back. So it means that I know who's the destination, who is not sending a keep alive back. So I can jump into that particular router and I can see my BGP config. But you can since enable your BGP keep alive in the router, but that is a router intense task, so it will keep sending your BGP. So it's always better to use Wireshark to capture that, because when you have problem only then you're going to look into your all your TCP keep alives. So it is always suggested to do a capture with Wireshark. Yeah, now let's see what is EIGRP and what by design and how Wireshark interprets those values. So now let me give you a little bit background about EIGRP. So here, I mean, EIGRP is not using TCP, anything like that. So EIGRP is a routing protocol. All it does, to make the connection active, it sends some hello packets. But I'll give you a background about EIGRP. So this is complete in IGP protocol that is used within your autonomous system, your office, that cannot be routed in the public. So example, this is your EIGRP hub, and this is spoke. So this is your DMVPN hub example. So I make a neighborship with all the CHRP. The DMVPN stands for dynamic multi-point VPN. So why this is widely used? Um, Example, if I want to make a tunnel with a spoke, it's a dynamic tunnel. So it's a dynamic tunnel between the spokes. So from the hub, it makes a tunnel back. And with the Wireshark, how I'm going to troubleshoot the EIGRP. So for that, I'll open a active capture. So the very first thing is first we should have a routing. Then it will send all its updates to its multicast address until it forms the neighborship. And if you look at this, what are the values it shares? So it says I'm running Cisco EIGRP and the version, and it is an hello packet, and my checksums are all good. And if you see the soft version of EIGRP, it's version 12.4. And if you look at this parameters, EIGRP, it make use of this K values. So we are not doing a deep dive about EIGRP, but I'm telling. So here you can see your hold on time, So it waits for 15 seconds. If I'm not getting a hello, it will wait for 15 seconds. And it's talking about its autonomous number system. So my autonomous number system is 100 and it has to be same on both end. Otherwise your neighborship will not form. And from 10002 to 10001, if I look the update and it says my autonomous number system is 100 and it says my version is 2, and if you look at here the EIGRP update, so once it sends an updates to the multicast address, once the neighborship is formed, it's going to show me the internal route information, the NLRI information. The prefix length is 24 and the destination is 192.168.4.0 network, and this is my prefix length, and it shows about my delay, my MTU, and if you see MTU mismatch, you can figure out that your reliability load, all this are EIGRP matrices. So EIGRP uses the delay and bandwidth, MTU. So you can see all these values here. So this is an hello acknowledgement. So there is definitely a connection between these two. So you can compare the parameters, what all the parameters I have, and is it matching? So you can even see the internal route information, your next stop details, your prefix length, what is the network that's been advertised. You can see everything in EIGRP, but it is not using TCP. So this is something once both the source and destination, it sends all its update in the hello updates. It sends to the multicast address. So once the neighborship is formed between source and destination, it's going to exchange all its information between the source and destination, not with the multicast. So if there is an update, it sends as I know hello and it sends an update. So inside the update information, if you look at this, it sends to the multicast status as something in my topology, I have changed something, and this is an update. So what is the update? And the route information, whatever it's been changed, it's going to advertise the same. So you can also see the bandwidth here. It's pretty useful when you do a troubleshooting. You can compare. So all the values, whatever you have given, is it successfully happening on both end? That's again give you a bird's eye view about the complete EIGRP process here. So now let's do a lab for EIGRP and let's take a capture and let's see how what exactly we see there. So I'm going to reload this. So in the meantime, even the Wireshark in the Wireshark, we see if there is a soft reset. If we are doing a soft reset, it's going to acknowledge that some soft reset happened. Is it something in the software level you give clear IPv GP routes? So once you do that, you even get that information. Somebody the remote ends a 1.1.1. It's I mean the router the route originated from 1.1.1 that's been they have been BGP soft reset there. So this is a comparison for hard reset and soft reset. If you see this, so because it is a hard down, then again it's a sin. For the sin, I got a sin act back, and I got I'm acknowledging it back, and I see the open message and everything. So this is hard reset. That's something somebody they did an admin up and down on the interface. So that's the difference between router refresh and this hard reset. Even you can see those information in Wireshark. Okay, so still it's there. Show run section BGP. So I'm going to give an autonomous number system 10 and the network to show run. What did I give here? Autonomous number system 10, and I'm going to advertise my network. I'm to calculate the wildcard mask for the same. So it's for slash 24. So router EIGRP 10, no auto summary. So I have turned on my debug. And at the same time, I'm going to do a capture. So who is sending a SIN? So 10001. So let's see, where is 10001? I'm still running BGP. So it's a good closer. I keep sending SIN, but I'm not getting a SYNAC back. And 10002, it resets the connection back because I'm not running BGP there. You can see the reset flags. So it's an indication that, okay, the remote end is not running BGP. So 10002 is resetting and it sends an hello. So it says the EIGRP version, the autonomous number system, what I'm running. Since I didn't establish a connection, so I'm not sharing I'm not sharing my NLRI information here. So I'm going to this router and I'm going to give no router BGP1. So if I give show run section BGP, if I do a debug EIGRP packets, so router EIGRP, let me give an autonomous number system 60 and I give show IP interface, show IP interface, show IP interface brief. So I'm running 10 network and 11 networks. So router EIGRP 60. So my network is 10.0.0.0 and my wildcard mask do show run interface fastest than 0/0. So my network would be 10.0.0.0 and 0.0.0.255 and 11 network. The subnet mask for /32 is all zeros because that is my loop back. Oh, sorry for that. So my network address is not correct. Okay, let's see what I see here. Show IP route, EIGRP, show IP route. So what I see here, so still I didn't form a neighborship here because my autonomous number system is incorrect. Show run section EIGRP. So it is still sending in hello. Both are sending in hello to the multicast address. So I'm going to change the network, my NLRI, and I see the adjacency is up. And if I give show run section EIGRP, so I'm running two EIGRP process. So I'm going to delete router EIGRP 60. Config router EIGRP 10. I have to turn off auto summarization, no auto summary. If you see now, I can see an update that's been exchanged between 10.0.0.2 and 10.0.0.1, and I can see the autonomous number system. So earlier my autonomous number system is incorrect, so I didn't form a neighborship at all. IP dot address 10.0.0.1 and IP dot address equal 10.0.0.2. So this is all the BGP connections earlier. So I'm not using the BGP anymore. So now I don't see any SYN packets that's been exchanged. All I see is only EIGRP. And then from both, it says my autonomous number system is 10. show IP route. So it prefers the directly connected show IP route. EIGRP neighbor. So hold on time is 12 seconds. And I see the interface where I configured, so where my active BGP connection has been established. And I can see the same thing here. And also you can differentiate your acknowledgement. It says acknowledgement 1, acknowledgement 2. So whatever the information that's been exchanged, it's showing what is the acknowledgement number for the same when I got an update for the same. So that's it about EIGRP. So you can dig deeper with other captures and you can do a troubleshooting there. You can figure out exactly what else you can figure out. Even the NLRI information will be exchanged. But this is just an overview of how exactly the Wireshark interprets the EIGRP. With a lot of capture and practice, we can troubleshoot more with EIGRP and BGP.